This is going to be my tutorial video on XORing, or the use of the exclusive OR logical operator. After a lot of work on my next solutions video, I couldn't find a way around first having a full tutorial out on XOR because it's going to be rather important. Diving right in, if you don't know what a logical operator is, just think of it as a process designed to alter binary in a logical way. Most basic operations done by your computer use these logical operators to change memory. If you want to learn more about them generally, you can look up logic gates, but here's the particular logic behind XOR. So, treating 1 as true and 0 as false for the bits. XOR is true when and only when one or the other of the two input bits is true. That means if both of the input bits are true or both of the input bits are false, our output will also be false, therefore 0. This thing is called a truth table, and it's just a way of representing some digital logic. It has all of the different input and output options on it, so you can see the full path of bits coming into this operator. So I'm going to show you some examples of this working, as well as provide a script that you can use to play around with this in a visual way. I'm also going to add a skip here to where we explain why this matters to cryptography later on. So I'm going to fill a couple files with some random characters here. You'll see them on the right. There's 3 files. And I'm going to show you what XORing them together looks like down to a bit level. So let's take 1 and 2 here. If you take a look at the output and consider the logic we talked about above, you can see the operations being done on each pair of characters. It goes bit by bit, compares them using the logic above, and decides on an output. As always, if the result is 1, it means only one of the 2 incoming bits was true. The /x05 thing at the end just means that the general output when all of this is done isn't actually an ASCII readable character. It's binary that doesn't really represent anything in that readable space. So I'm going to show you a different example where that's not the case. We're going to take file 1 and file 3 here, the inputs being ABC and 1, 2, 3, and strangely enough, all of the outputs of all of these different XORing are the letter P. And this is where we start to see why it might be useful in cryptography. We had all of these different combinations of characters that ended up with the same end result, without any evidence in this string of 3 Ps what the original pairs of strings that went into it might have been. I'll link to a table of the ASCII readable characters and their bit representations below, just in case you want to play around with that a bit yourself. So let's talk about why this is important to cryptography. There's several really important features to the Xor tool. It's mainly that it's reversible, as well as the interesting way that it is reversed, that it's commutative, and that it's associative, and I'll show you what all of these mean. XOR being reversible is what lets us use it like a cryptographic key, like the encryption and decryption steps of a classical cipher. It just means that anything we do with XOR can be undone to get the originals back again. So we're going to take 2 files and we're going to XOR them together. We'll put 1 XOR 2 as the file name, and I'll show you that file as well. It's 3 kind of useless characters. Now, of course, there's going to be a way to restore this to the files that were used to create it, and it's starting to show an interesting quality of XOR, in that it's kind of its own reversal. Let's say we want to get file 1 back. If we repeat the step of XORing in file 2, it undoes the changes that file 2 did to this, and gives us just what's left, which is just our file 1. Now, we get into what I mean by XOR being commutative, in that the order of operations doesn't matter. You can do it in a lot of different ways, which means in this combined file of 1 XOR 2, we can also get back file 2 by just XORing that out. So that's a pretty simple example, so I'm going to show you a little bit more complicated one. It also gets into the associativity of XOR as well. We're going to take 1 XOR 2, and we're going to XOR in file 3 for this output, which is all 3 of these all XORed together. It's this big combined file. Now, opening it, entertainingly, all of these XORing steps actually did give us 3 readable ASCII characters. Looking at these 3 characters, like our P file from earlier, you wouldn't really assume that all of these different strings are all obtainable from this one set of characters. Now, I'm going to do a couple other steps here, and make a few more files that we'll want to use in this bigger example. I'm going to XOR file 1 and 3 here. I'm going to XOR 2 and 3. We've already got 1 and 2. And now I can show you some of the really interesting properties of XOR. I'm going to take this combined 1 XOR 2 XOR 3, and we're going to take file 1 out of it. Logically, that should give us the same as 2 XOR 3. Despite being made a different way, it should be identical to the 2 XOR 3 that we generated from 2 files earlier, and I'll show you that it is. Now the more interesting feature is kind of the other way of this, in that we can actually take our 2 XOR 3 and assume that it's the same as XORing in 2 and XORing in 3, and we can just take our big combined file, XOR it with 2 XOR 3 there, and get just back file 1, because it undoes both of the steps that we did with 2 and 3. Now, I'll show you some other ones. We can do the same sort of thing to get file 2 out. We can do this to get file 3 out. For completeness, if we take our big combined file and XOR out only file 2, there's those 3 P's again we saw right at the beginning when we XORed file 1 and 3. So despite the different processes being utterly different and all of the steps we took in different orders, because of the different interesting qualities of XOR, it all logically ends up at the same place, just XORing in and out these files from the equation, canceling itself out to give us back only the file that we want, because XOR is sort of its own inversion here. All of these files remain the entire time, only 3 characters long, and yet here's all of these different things that we can get back out of it. Now, this obviously goes to make XOR just fascinating from a cryptography perspective, because given a giant useless binary file, there's really no way to know how many useful things are possible to obtain from it. But with the right XOR key, you can get just tons of different things back out of it. It's really the natural evolution of the classical ciphers, but in the end I would say it's quite a bit more powerful.